You are floating in a spaceship, drifting towards something you cannot quite see. Not because it is hidden, because it swallows every photon that comes near it. Your instruments read a mass millions of times heavier than your sun, compressed into a point smaller than a city. Your ship creaks, your pulse rises, you check the distance again. Still falling, still calm, for now? What do you think happens first? Alarms? Darkness? A flash of light as the universe says goodbye? The real answer is far stranger than anything a movie has shown you, and it starts with your feet. Your feet, if you are falling in feet first, are closer to the black hole than your head. That sounds obvious, it sounds harmless, but gravity does not treat your feet and your head equally. The closer something is to the black hole, the harder it gets pulled. So your feet accelerate faster than your head. The gap between them stretches. Your body, every cell of it, becomes caught in a tug-of-war between two different strengths of gravity acting on the same frame. Physicists have a name for this, and it is somehow both playful and horrifying. Spaghettification. Your body stretches, thread by thread, the same way dough stretches under a rolling pin, except nothing is rolling. Space itself is doing the pulling. Not a force reaching in from outside, but the geometry of the universe itself curving so sharply that straight down and further down become two different directions with two different intensities. Your spine becomes a battlefield between them. Karl Schwarzschild, a German physicist working out equations while serving on the Russian front in 1916, was the first person to solve Einstein's field equations precisely enough to describe this effect. Picture that for a moment. While artillery fire echoed nearby, he was calculating exactly how spacetime would curve around a perfectly spherical mass. He mailed his solution to Einstein, who was reportedly astonished that such an exact answer could be found so quickly. Schwarzschild never saw a black hole. He developed a rare autoimmune disease during the war and died within a year of publishing his solution. But his math still describes, with unsettling precision, the exact radius at which nothing, not light, not sound, not you, can turn back. That radius has a name too, the event horizon. Cross it, and the word outside stops meaning anything for you ever again. Here is where the story gets stranger than most people expect. If the black hole is small, say a few times the mass of your sun, spaghettification kills you long before you reach the event horizon. Why? Because a small black hole packs its mass into a tiny volume, which means the difference in gravitational pull between 2 points, just a couple of meters apart, roughly the length of your body, is enormous. The stretching forces near a small black hole are so extreme that your body would be pulled apart within a fraction of a second, still outside the point of no return. You would never even get the chance to cross the horizon intact. Death arrives before the darkness does. So why do documentaries always show astronauts drifting calmly toward a black hole, seemingly unharmed? Because most of those depictions, whether they know it or not, are describing a supermassive black hole, not a stellar one. But what if the black hole is enormous? Supermassive, the kind sitting at the center of galaxies with a mass equivalent to millions or billions of suns. Here the physics flips in a way that feels almost unfair. The bigger the black hole, the gentler the stretching near its event horizon. Cross the horizon of a supermassive black hole, and you might not feel anything unusual at all. You could sail through the point of no return sipping water from a pouch, and your instruments would show nothing dramatic. No barrier, no wall, no sensation of crossing a line. Isn't it strange that the deadliest object in the universe can also be the gentlest one to enter? This is the part your gut refuses to believe. Falling into a black hole does not feel, in the moment, like falling into anything at all. It feels like empty space, continuous, boring, ordinary space, right up until it isn't. Because the stretching does not disappear, it waits. As you continue falling inward, the gravitational difference between your head and feet keeps intensifying, moment by moment, until eventually it becomes unbearable, and then it becomes total. Your body separates into a stream of particles, then atoms, then something closer to a ribbon of matter than a person. Scientists describe this final unraveling with a kind of clinical distance, but the physical reality is total dissolution. Now here is where the paradoxes begin, and where even the physicists who study this for a living start to sound uncertain. What does an outside observer see happen to you? Not what you experience, but what someone watching from a safe distance, say a colleague back on your mothership, would actually witness. They would never see you cross the event horizon. Not ever. As you approach the horizon, the immense gravity stretches time itself, a phenomenon called gravitational time dilation. To your colleague, you would appear to slow down, then slow down more, your image growing redder and dimmer as your light gets stretched to longer and longer wavelengths until you seem to freeze forever on the edge of the horizon, fading like a photograph left in the sun. From their point of view, you never quite finish falling in. Meanwhile, from your own point of view, nothing freezes. You cross the horizon in ordinary, finite time, feeling every second pass normally, unaware that outside, you have become a ghost of light fading into invisibility. Two true stories about the same event, depending entirely on who is watching. Does that sound impossible? It is one of the reasons Stephen Hawking spent decades of his career obsessed with black holes, not because they destroy matter in some simple sense, but because they seem to break the rules about how information should behave. In 1974, Hawking proposed that black holes are not perfectly black at all. They leak a faint stream of radiation, now called Hawking radiation, caused by quantum effects near the event horizon. Over unimaginable spans of time, this radiation would cause a black hole to lose mass and eventually evaporate completely. Which raises the question that kept Hawking arguing with fellow physicists for the rest of his life: if a black hole eventually evaporates, what happens to everything that fell into it? What happens to you? Does the information describing your atoms simply vanish from the universe, violating one of physics' most sacred rules, the rule that information can never truly be destroyed, or does it somehow escape, encoded in that faint trickle of radiation, scrambled beyond recognition but never truly erased? This is called the black hole information paradox, and it remains unresolved. In 1997, physicist Leonard Susskind and others proposed an idea that sounds almost like science fiction but is treated seriously in modern theoretical physics, that everything falling into a black hole might, in some sense, also be smeared across its event horizon, encoded on that two-dimensional surface like a hologram. If that idea holds up, then the person falling in and the information about that person might exist in two places at once, described by two different but equally valid pictures of the same event. Would that mean two versions of you exist, one falling forever inward and one painted across the horizon surface? Nobody knows for certain. You would become, quite literally, one of the most debated open questions in modern physics. For a long time, black holes were purely theoretical, elegant solutions to equations that some scientists doubted could exist in nature. Even Einstein himself once expressed doubt that anything so extreme could form from real physical matter. That changed in dramatic fashion in April 2019, when the Event Horizon Telescope collaboration, led by astronomer Shepard Doleman and involving hundreds of scientists across a global network of radio telescopes coordinated to work as a single Earth-sized instrument, released the first direct image of a black hole's shadow at the center of a galaxy called M87, 55 million light-years away. The image showed a glowing ring of superheated gas circling a dark void exactly where the equations predicted it should be, a silhouette cast by an object with a mass billions of times that of your sun. For the first time, humanity was not imagining a black hole. It was looking directly at one, and the picture matched a century-old equation almost perfectly. So picture yourself again, in that ship, drifting toward the horizon of a supermassive black hole. The stretching has not started yet. Your instruments show smooth, uneventful space. You glance at your monitor and see your colleague's transmission from the mothership, already lagging, already growing fainter, their voice stretching into something slow and low, like a recording played at the wrong speed. You wave. From their side of the universe, that wave never finishes. You keep falling. The tidal forces begin as a faint discomfort, a pulling sensation you might mistake for turbulence. Then it intensifies. Your body starts to stretch, and there is no version of this story where that part stops. Long before you would reach any singularity, any final point where the equations themselves break down and stop making predictions, you are gone. But the story does not quite end there, because in this universe, the information that made up your body did not disappear the moment you did. Whether it escapes billions of years later in Hawking radiation, or remains locked in some deeper structure of spacetime we do not yet understand, is one of the last true mysteries sitting at the intersection of gravity and quantum mechanics. You would not be erased from physics. You would become a question mark physicists are still trying to answer. And that is the real reason this story keeps pulling people in, long after the initial fear fades. It was never really about the horror of being stretched into a thread of matter. It was about a single spaceship drifting toward the one place in the universe where the ordinary rules of cause and effect stop applying cleanly, where two observers can watch the same event and see two irreconcilable truths, and where your own atoms might outlive the black hole that consumed you. You started this journey wondering what would happen to your body. You ended realizing the more unsettling question was never about your body at all. It was about whether the universe keeps its promises, even at the edge of the abyss.